Okay, this will be Chapter 6, Lesson 3, and we're going to begin talking about something called the Heisenberg Uncertainty Principle. And this is more of a theoretical idea that we won't do too much with, but what we found is anytime you want to look at matter at a very microscopic level, on the level of atoms and electrons, some strange things begin to happen. In fact, a lot of the laws that we're used to at our level, at the macroscopic level, are not followed down at the microscopic level. So this principle says you cannot know both the position and the momentum, which is essentially the velocity or the speed of a particle, together. In fact, the better you know the position, the worse you know the momentum. By the way, momentum, if you don't know, is mass times volume from physics. So this is the change in position, and this is the change in momentum. And there's an interesting equation that has the Planck's constant, which you've seen before, and 4 pi. This is just 3.14, the standard pi from math. So all we have to say here, we're not going to do too much. You could do some calculations with this equation, but all we'll say is that a lot of times it's difficult, really difficult for us to pinpoint and predict exactly where the electron is because of this uncertainty principle. It's essentially a limit to knowledge. It's really strange, but if you research this uncertainty principle, a lot of very strange things and ideas start coming up. So this carries us into something called quantum mechanics. And there's a guy by the name of Schrödinger who essentially developed the math to deal with this idea of both waves and particles. Because we said last time that all matter can be thought of as a wave and a particle. But this especially is true of subatomic particles, atoms, especially electrons. They definitely exhibit both wave and particle like natures. So we have to consider this as we think about the electron and how it moves around the atom. So this is known as quantum mechanics. So this Schrödinger guy, with an interesting name, proposed a bunch of equations. And technically these equations are pretty advanced. You'll actually need calculus to kind of solve them. But what they give you is functions or graphs of where you can find the probability of electrons, and these probability functions are called orbitals. And you may recall orbitals from Chemistry 1, and that's essentially the idea that how we got these orbitals. So each orbital essentially describes a spatial distribution of electron density. This is saying that each orbital can be graphed. These equations, the functions that he came up with, can be graphed to give us roughly a three-dimensional distribution of electron density. If all this sounds a bit strange and theoretical, don't worry too much. We're not going to require too much of this idea on the tests and so forth. Oh, here we have a little bit of trouble. And this is Schrödinger's wave equations. These are the wave equations. Don't worry too much about them, but they're not even showing up. So that's probably a look into our future, that we probably will not be dealing with them. The orbital idea is important, however. So there are principally three orbitals that you should know the shapes of. The s orbital, which is spherical, and so this is spherical, and every energy level has one of these, one s orbital. There are p orbitals. These are oftentimes called dumbbell shaped, and there are three of them. The three actually coincide with the three dimensions of a three-dimensional plot, or three positions. So the up, down, left, right, and in and out. This is the x, y, and z axis if you graph in 3 dimensions. Next we go to the d orbitals. The d orbitals, there are 5 of these, and they also orient themselves in the plane, this x, y, z plane, and then there's a strange one. That this guy here is a bit strange. No need to necessarily be able to reproduce these, but it's a good idea to hold on to the shapes of both the p and the s orbitals, as the atoms will be interacting through these orbitals, forming bonds, and it'll be important for us to understand how this is done. So these orbitals then exist in sublevels, also known as subshells, and then the shells then exist in or subshells exist in shells or energy levels. So this is kind of, we're talking about it backwards, but a shell then is broken up into a subshell, which is broken up into orbitals. And here, if you want to know how many sublevels there are in each energy level, it's just the number of the energy level. So energy level 1 has 1 subshell, 2 has 2, 3 has 3, and so on it goes. If you want to know how many electrons you have in the energy level, there's a neat equation here, in the equation 2n squared. So if you plug in for n, say 3, say we want to think about energy level 3. If you plug 3 in, 3 squared times 2, 3 squared would be 9, times 2 gives you 18 electrons. So 18 electrons exist in the third energy level, and that's how we go about it. And then each orbital can hold a maximum of 2 electrons. So, and the reasoning for this is because electrons have something called spin. This is an energy state they have, which gives them a slight difference in energy. So you could think of it as kind of spinning on its axis, kind of like the Earth spins on its axis. It's not exactly this, but good enough for our understanding. The spin state could be positive a half or negative a half. So 2 electrons then will go into each one of these orbitals. So if you recall, a visual way of thinking about this that helps, say, your p orbital, you can think of 1 electron in each lobe of the orbital, even though both electrons actually can exist in both sides of this. So, but that's essentially kind of the idea. And interestingly enough, you can actually see this pattern and this organization on the periodic table. And the periodic table was organized in a way to actually reflect this idea of subshells, shells, and orbitals. So, for example, if you have shell number 2, shell 2 has 2 subshells. Subshells will be your S and your P subshells. And what you see is here is the second energy level, and you have a 2S and you have a 2P subshell. In 3 you should have 3, so you have 1, 2, and 3 of them. And then the amount of orbitals in those subshells, the S, remember, had 2 orbitals, the P had 3, I'm sorry, the S had 1 orbital, 2 electrons. Let's try that again. The S had 1 orbital, the P had 3 orbitals, and each orbital can hold 2 electrons. So what you see then is every S subshell holds 2 electrons all the way down. This is the S block in the periodic table. Every P subshell has 3 orbitals, each with 2 electrons. That gives us a total of 1, 2, 3, 4, 5, 6 electrons in every P subshell. And then the same thing with D. If you count, there will be 10 in D and 14 in F. So if you study the periodic table's organization, it reflects very interestingly this idea of orbitals and subshells and shells, which tells us that we've got our theory right. Okay, so a quick little question. How many subshells, orbitals, and electrons are possible for energy level 5? So let's go ahead and break it down and see what that gives us. So we got shell 5, let's call this shell 5. Our subshells, we'll have 5 of them, because remember, you get the same number of subshells as you have shells, and your subshells are the S, the P, the D, the F, and then after F you go on down the alphabet, G, H, and so forth. Those are your subshells. Your orbitals, remember, the S has 1, the P has 3, the D has 5, the F has 7, and then if you follow the pattern, G has 9. So what we have is, for a total of subshells, we have 5 subshells, and orbitals, you got 9 plus 7, 16 plus 5, 21, plus 324 plus 125. So we have actually 25 orbitals. If you want to know how many electrons we have, it turns out that each orbital can hold 2 electrons. So if we take this number and technically multiply it by 2, we'll get ourselves 50 electrons total. Can fit into the 5th shell, or the 5th energy level. What you can also do is you can actually use that equation 2n squared. So since our n is equal to 5, plug 5 in, you get 5 squared times 2. 5 squared is 25 times 2 gives you 50 again. So you'll see how this simple equation gives you the number of electrons in any shell. This is pretty interesting that math works so well, and this is why we say math is the language of science. And that will be it for lesson 3.